Hello Math 1093, this is Dr. P with Double and Half. In this video we're going to talk about how to use the sum of angle identities that we've been using in the last couple of videos, these for sine and cosine, to come up with, so we're going to use these to come up with formulas for sine of 2t and cosine of 2t. And this is actually kind of cool because these two expressions here, these are formulas that get used in calculus all the time. They get used especially for integration. Now, all of that may be sort of foreign to you right now. You might not know what this is leading to, but trust me that these formulas are quite useful. Okay, so in this video we're going to talk about how we develop those just using what we know about the sine and cosine functions. And I actually noticed already that there's one problem here, and this, I did not make this a plus, so let's make that a plus. Sorry about that. Okay, there we go. Those should both be sum of angle identities. All right, so anyway, what is sine of 2t? Well, one way of thinking about this is to rewrite this as sine of a sum of two angles. Well, how do I write 2t as a sum? Well, 2t is equal to t plus itself. Okay, this is maybe using the letter t was not the best choice of variables, but I think I'll be able to get out of that pretty soon. All right, so at this point I've got this written as a sum of two angles here, t plus t, sum of angles. So now I'm going to call this one alpha and this one beta, and I'm going to use my sum of angles identity for sine on this. So using that formula, I get that sine of t plus t is equal to sine of t times cosine of t plus cosine of t times sine of t, because both alpha and beta are equal to t. And well, cosine of t times sine of t is the same as sine of t times cosine of t, so that's really just sine of t cosine of t plus another sine of t cosine of t, and that's equal to 2 sine of t cosine of t. Okay, so I get one formula. One formula that I have is sine of 2t equals 2 sine of t cosine of t. And that is quite a handy one there. Okay, what about cosine of 2t? This one's also kind of cute. Cosine of 2t is the cosine of t plus itself. And that can be rewritten as, okay, so what am I doing here? I'm letting alpha and beta both be equal to t. And if I do that, then I get that cosine of t plus t is equal to cosine of t times cosine of t minus sine of t times sine of t. And that comes out to cosine squared of t minus sine squared of t. And that is one formula for cosine of 2t. But there are a couple of other ones that are a little bit more useful sometimes, because this one's kind of nice and elegant, but it involves two different trig functions. And sometimes we prefer formulas that use only one of the 6 trig functions. So could I adapt this formula to sort of fit that mold, something that uses only one trig function? And I absolutely could, because I know the formula, or I know the relationship between cosine squared of t and sine squared of t. I know that cosine squared of t plus sine squared of t, that is equal to 1. So I can rewrite either one of these in terms of the other one. So for example, I could say, well, sine squared of t, that's 1 minus cosine squared of t. And so I could rewrite this expression here. Okay, just trying to draw a little arrow here showing where I'm going. I could rewrite this as cosine squared of t minus 1 minus cosine squared of t. And then that would be cosine squared of t minus 1 plus cosine squared of t, which is 2 cosine squared t minus 1. Okay, I could also start with cosine squared of t minus sine squared of t, and I could instead rewrite cosine squared of t as 1 minus sine squared of t. That would give me 1 minus sine squared of t minus sine squared of t, and that would be 1 minus 2 sine squared of t. So I get this master formula that actually has like 3 heads, like a Cerberus. Cosine of 2t is equal to cosine squared of t minus sine squared of t, which is also equal to 2 cosine squared of t minus 1, which is also equal to 1 minus 2 sine squared of t. All of those things are equivalent. And so I sort of think of this formula as encompassing all of these different forms here. Okay, so now what I've done is I've developed what I call double angle identities for sine and cosine. This is a double angle identity for sine, and this is a double angle identity for cosine. Okay, so now what I want to do is I want to show something else kind of cool that we can do with this information. So I want to focus for now on the cosine of 2t. All right, so one thing I can do with this formula is I can rewrite it. I can focus on, for example, the fact that cosine of 2t is equal to 2 cosine squared of t minus 1. And now I'm going to do a little bit of rearranging here. I'm going to rearrange so that I have, let's see, first I'm going to just switch the two sides of the equation. And then I'm going to add 1 to both sides. And then I'm going to divide both sides by 2. So cosine squared of t is 1 plus cosine of 2t over 2. Okay, the fact that I switched those two add-ins, there's no real significance for it. It's just something I habitually do when I do this calculation. Didn't have to be done. Okay, cosine of t, therefore, okay, if I know that the square of it is equal to all this stuff, then cosine of t has to be the square root of all of this stuff. So that means cosine of t is the square root of 1 plus cosine of 2t over 2. Except, one thing to remember, if I have the square of cosine of t equal to all of this, then that means that cosine of t needs to be either the positive or negative square root of 1 plus cosine of 2t over 2. All right, so really important to remember that is that there needs to be a plus or minus there. Okay, so what does this mean? Why would I be doing this? Well, one thing that I could do is I could let t equal 1/2 of theta, and then rewrite this formula as cosine of 1/2 of theta is equal to plus or minus the square root of 1 plus cosine of 2 times half theta. Well, 2 times half theta is just theta over 2. And now I have a formula for the cosine of 1/2 of theta. This is called a half angle identity for cosine, which is kind of nice. Now, why is it that I can't write down a formula without having this plus or minus in there? In other words, I mean, if I just want to find cosine of 1/2 theta, shouldn't I just be able to figure out what that is in terms of all of this other stuff without the ambiguity here? Like, it feels like having this plus or minus here means that I can never be quite sure of what cosine of 1/2 theta is. And actually, that's kind of true. I really do have that ambiguity there. And the reason is, I could picture a couple of different scenarios here. So I'm going to give an example. Suppose I wanted to use this idea to find the cosine of, let's say, 15 degrees, first of all. Okay, so if I want to use my half angle identity for cosine to find the cosine of 15 degrees, well, that's going to be plus or minus the square root of 1 plus cosine of, well, let's see, what is this anyway? 15 degrees is 1/2 of 30 degrees. Okay, so I'm just doing that to illustrate that this should be the cosine of 30 degrees inside the formula here, all over 2. Okay, and what would that be? That's either plus or minus 1 plus, and then cosine of 30 degrees is like root 3 over 2, and then all of that over 2. So I get plus or minus this square root, which is kind of ugly, of 1/2 plus root 3 over 4. I'm just distributing this factor of 1/2 here, okay? And that's kind of gross. There's actually a nicer form for it, but I want to focus on this issue of plus or minus for now. Okay, so is it the plus or the minus? To figure that out, I just have to realize that 15 degrees is in the first quadrant. So its cosine is going to be some positive number. It's not going to be a negative number. It's going to be positive. So in this case, the cosine of 15 degrees has to be the square root of 1/2 plus root 3 over 4. Okay, and again, there is a way to write that without nested square roots, but I'm not going to mess with it right this minute because I want to talk about another example here. So what if I wanted to find out the cosine of 195 degrees using the same idea? Well, 195 degrees, that's kind of a weird number I picked, but it's exactly 1/2 of 390 degrees. So the cosine of 195 degrees would be 1 plus the cosine of 390 degrees, whatever in the world that is, all over 2. Well, what is the cosine of 390 degrees? 390 degrees is in the same position as 30 degrees. Okay, so again, here I'm going to get, and now that should have a plus or minus on it. Sorry about that. So this is going to be plus or minus the square root of 1 plus root 3 over 2, all over 2 again. But this time, I'm talking about the cosine of 195 degrees. 195 degrees is just a bit past 180, and it's in the third quadrant. So that means that when I calculate this square root, I'm going to be taking the negative square root. All right, and that's even though this 390 degrees, it's all the same calculation as what I did earlier with 30 degrees. 30 degrees and 390 degrees are in the exact same spot on the unit circle, but the calculation ends up being different because the thing I'm calculating is entirely different. These are in totally different quadrants here. So that's an illustration of why this formula here, the half angle identity, needs to have a plus or minus in it. I can't decide that until I understand what angle I'm working with here. Okay, so the purpose of this video was to show how we come up with the double angle identity. That's just using the sum identities from earlier. So I'm trying to get all this in the same frame, but it might be counterproductive to do so. Anyway, I illustrated how to get sine of 2t and cosine of 2t, and then showed how to use that to get what we call the half angle identities. You're going to want to read more about these, and we're going to cover some more in class, but that's an intro to double and half angle identities.